And see here, I should be able to. Yes, okay, I think we're good. Why don't you go ahead and use this? All right, so the format here is going to give each panelist about 5 minutes, and then we're going to open it up for free Q&A after that. And I told them they could talk about anything they wanted, although we have a theme, they don't have to specifically stick to that theme too closely. All right, go ahead.
Yeah, thank you. Hi, everyone. So I will try to give a little bit of a perspective on the, let's say, optical version of spin simulators and annealers. This will be the lasers, the maybe polaritons, the generate OPOs. And this comes only from being close to my own work. So why is that here? Okay.
We can see it up there.
Yeah, I can't. Okay. So what you can see here is the hope that coupled lasers, where each laser has a phase, say between 0 and 2 pi, can map somehow to a spin system, where each spin, let's say XY spin, is oriented. And this is the motivation to try to build a spin simulator based on lasers. This will be XY spins. I just mentioned there's a rather large variety of these annealers. I think some of them are represented here in this audience. Some of them are a bit exotic. I painted in green the laser one because that's what I do, but others are also interesting. And just to show you that it's a really very broad field, this is another work we do where we coupled violin players and we show that they can find minimum of XY Hamiltonian. They can even overcome frustration better than coupled lasers. So they do better. And this is a colleague from Weizmann that shows that ants can solve Ising Hamiltonian when they do optimization and somehow find bilocal interaction. So this is really a broad field. And what I'm asking is what are the prospects and what are the limitations of these approaches? And these are all rather classical systems. So I have a list of topics and I'll just touch each one of them and I'll leave place for comments later. So a big question is how exact is the mapping? And the answer is it is not, at least for the lasers. And this is an example of a recent paper that we published where on the horizontal axis, you can see the homogeneity of the intensity of the lasers. And on the vertical axis, you can see the difference between the state that the laser finds by what is called the minimal loss solution, because the lasers are coupled dissipatively, and the XY minimal energy state. So when they are the same, this means that the laser solver finds the right XY solution, but it only happens when the intensities are identical. And this is actually not trivial to do. Tomorrow I will discuss it a little bit in more detail, and I will show that even identical lasers, when they are coupled in a general way, cannot have identical intensities. And if you try to feedback them, this turns out to be actually an NP-hard problem in general. So that's already, we are limited. Of course, this is a famous question. If you want to solve hard problems, the landscape, in this case, it's the loss landscape rather than the energy landscape as a function of the laser phase, but this is done, let's say, in a 1,000-dimension Hilbert space. It's rather complicated. You want to find the minimal global minima. And of course, there are many, many other minima, exponentially many. Some of them are exponentially close to the minima that you want. So there's the famous slide taken from Yamamoto group saying that for the laser, you take a gain which is below the minimal loss. So the laser doesn't raise. You raise it slowly until it touches the minimal point. And then only this minimal global minima becomes macroscopic. Of course, to make this happen, you have to do this transition exponentially slow. So this cannot happen. And actually, no one really studied this dynamic carefully so far, including us, for many reasons. So this is another open question in the field. In general, what people do with these solvers, they either do heuristic, which is fine, or they do numeric. And here I'm showing you a typical graph taken from a Nature Physics review that you can see comparing many different solvers. But of course, this is problem dependent, as we already heard this morning, and you can get actually opposite results for opposite problems, and there is a correlation between the machine and the problems chosen by the people working with that machine to show that the machine works well. I think there is place to more rigorous mathematical description. This is one example I find from Weitzman colleagues, and these two people, the last authors, Eliran Sabag and Ofer Zeitouni, are actually real mathematicians that write lemmas and prove them. And even though there's a lot of simplification that they do, so they go a little bit away from the physical system, they use spherical spins, it's more convenient for them, but they actually get some very interesting results. And in particular, they study the complexity of the system as a function of the nonlinearity, how much you go above threshold, which is something that we are all interested in. And they do it with mathematical curves. So I think more of this is really desired. Scaling is, of course, always important. One question people ask is how many spins we can simulate. So this is an extremely impressive experiment done by NTT, inspired by earlier works by Yoshi Yamamoto, and they reached 100,000 spins. But remember that the fact that you have 100,000 spins talking with each other all to all using this FPGA, huge and very expensive network, doesn't mean that you actually get this long-range coherence. And actually, when they publish results of how many spins are really correlated, it goes by, let's say, 10, 20, 50. So it's not clear that you really gain a lot from going to all this scale. Also remember that as you do the scaling, the length of this loop grows to several kilometers, and that means that your clock cycle becomes quite slow on the millisecond scale. Our system is, let's say, a spatial machine. It's done with lasers, so it's an XY machine. It's a meter size, so it's faster by about a factor of 1,000, and it works in parallel in the spatial dimension. We cannot do 100,000. That's a bit hard for us, so we do typically hundreds or thousands, but one time we did 10,000. What is nice about our system is that we could actually show coherence between all the 10,000 spins true for an easy ferromagnetic coupling. So that's the easiest problem you can do. And the way you can count how many spins are synchronized or phase lock is by measuring the sharpness of the peak, actually very similarly to what Ulrich showed us before for cold atoms. So it's really very similar systems. Of course, these systems are limited by noise, or if you want, inaccuracies, and you really need to do good engineering if you want to scale them. So this is one example from our experiment. This is our coupled lasers. I won't go into details. I'll talk about it tomorrow, but you can see this device replacing one of the mirrors. This is actually a spatial light modulator, very common with experimentalists these days, and it gives you 1 million pixels where you can adjust the intensity and the phase of each one of them. So using this 1,000,000 degrees of freedom that you buy from Hamamatsu, you can do a lot of things. For example, you can correct aberrations to the lambda divided by 500 level. So that's something we could not do before. And once we are doing that now, this adaptive optics, we can actually get much better performance and much more control of the system. So we can reduce noise and reduce inaccuracies. At the same time, we notice that sometimes we like noise. So this is a simple example that you take coupled lasers on a ring with periodic boundary condition, and on the ring, the topology protects metastable states. This is very bad. If you want to find the absolute ground state, in this case, a ferromagnet, all these excited states are protected by the topology, and the system tends to get stuck. So what I'm showing you in this graph, this is an experiment we did a while ago. On the vertical axis is the probability to find the actual ground state, and on the horizontal axis, you can see how much we're above the lasing threshold. And it's well known that as you go closer and closer to the lasing threshold, noise plays a more important role in the system. And what you can see in this graph, that actually noise helps you. So the lasers, as opposed to XY spins, can find the ground state much better due to noise. It's everything. Yeah. I just want to mention that mapping to the XY spins means that we work in a discrete model, which we do most of the time, but sometimes we like to break out of this discrete model and we go to continuous because in the end we have an optical field. And when we do that, we go from, say, hundreds or thousands of lasers, we go to pixels on the SLM. So our degrees of freedom jump from 1,000 to 1,000,000 degrees of freedom. And this is an example. This Einstein and Newton modes of the laser are something that we can play. And we have actually now a very productive direction when we can solve continuous problem, which is the case for optics. So it's not like optimizing your stock portfolio, but it's doing things that optics like to do, and the optical computer does it for you. And I will stop here and not mention classical versus quantum because I'm out of time.
Okay, thank you. All right, Natalia, you want to come up and give yours next? When you get the microphone also. Is this you or is this?
Tornado. I got tornado warning on my watch.
Yeah, that's right. Is this you?
Yeah, that's me.
Okay,
Yeah,
good.
I really have one slide and the questions, so I was really hoping for immediate discussion.
Okay, let's see here.
But we just discussed with David that we had this panel over the COVID online 4 years ago, and I'm afraid the questions are still the same. Although we have many more systems that came, there was a tsunami of various optimization platforms enriched by electronic, optical, magnetic, spin waves, surface waves, Kerr solitons, etc., etc., etc. And of course, we have representatives of the most important platforms in this audience: Toshiba, NTT, spin waves, surface waves. Just mentioned Pbits as well. So all these platforms just came and claimed different advances. But what I really wanted to say, first of all, that again, this part of my talk really concerns optimization. So not universal quantum computer or quantum simulations for physics or anything. So I'm thinking about the using it for classical optimization. And then perhaps we have to think in terms of the common operational system. So truly aligned with operational system, meaning that we assign to the classical computer. So in this business, we all follow this pipeline. We start with real life optimization problem. We're trying to find an optimal solution of the function that lives in high dimensional space. We know that these problems, and this is mathematically rigorous fact, all of these problems can be mapped with just polynomial overhead onto the universal spin Hamiltonian, right? So it could be universalizing Hamiltonian or XY Hamiltonian or clock Potts Hamiltonian or K-local Hamiltonian. So the idea is that you map the variables onto the nodes of the graph, and then the structure of the function into the connectivity, interactions, couplings. And then your system tries to minimize something, minimize dissipation, find the ground state, minimize action, whatever physics is doing its physical magic. And by performing its relaxation, it actually finds a solution to your problem. And so from this perspective, now we can see what really we are missing. So from my point of view, again, we have a tsunami of different platforms. So first of all, how do we compare these platforms? How we estimate the strengths and weaknesses? The problem is that some platforms are better suited for some type of problems, but worse suited for some other problems. So there is no uniformity here. So which matrix for success we are choosing? And this is very intricate question. And, I don't know, one of us should write a paper one day, just proposing at least for the most standard Hamiltonians propose problems. I can give an example. So a lot of papers are being submitted with using Sherrington-Kirkpatrick, so all-to-all, random, normally distributed couplings, and then stating that, look, we go beyond JW limit, the usual limit 0.87 of the ground state. But this doesn't tell you anything, because actually the averaging properties of this graph, because you average over many instances, actually negate any problems that you have. So your method may fail, and I can give an examples on 3 spins, and I would also routinely give an example 3 spins or 8 spins. it fails. It doesn't solve this problem on 8 spins. But when you run it on 100,000 spins of SK Hamiltonian, the answer is better than some estimates. And so what are the matrix that we should introduce? They have to be very clear set of those. There is a lot of questions, but now we understand it much better, perhaps than 4 years ago, of mapping effect and hardware gains. For instance, we know that if we have k-local problem, we can map it on Ising, but there is an overhead, of course, and this superlinear overhead. There is an explosion of the coupling coefficients that degrades the performance. And at the end, any method actually will be much worse on if you do this mapping from k-local to Ising model that suggests that you need to implement k-local Hamiltonians natively. Even more so if then you have to map your Ising all-to-all onto the hardware that requires just the nearest neighbor interaction. You introduce another n-square mapping, another overhead, and that increases your annealing time by in average n to the fourth. So gives you very unfortunate scaling. So this is also very bad, and these things should be taken in consideration. On the other hand, there are methods now that you can actually go the other way from 2 local Hamiltonian to k-local, from 2 local to local, and reduce the number of spins. So this should also be taken into account. Again, how we compare different platforms if they use different bases. Some use kind of differential equations that describe the underlying physics. Some use some stochastic, like p-bits, some stochastic amplitude fluctuations, etc. Can we provide some theoretical guarantees? And there were questions during the lectures on this. Can we provide some theoretical guarantees for these methods? That also very often the method or platform is being proposed, but we really don't know the answer to this question. And then I went A, B, C, D because I copied 2 different slides and it didn't carry the number. Yes, so this is another set, perhaps again, talking about what do we mean by superiority and when do we say that one particular platform achieved the superiority over the classical computing? Probably never, but maybe for some very specialized problems that's can be achieved, or vice versa. You may think of a very intricate classical method for that particular problem, whereas you may have a machine that actually gives you sufficiently good solution in reasonable time for the wide class of problems. And there are other questions that also needs to be taken into account. And since we are facing this tsunami of new machines and new approaches, we better answer this question sooner rather than later. So that's my.
Someone else can go next. Slides, right? We can just stand up there and pick the microphone.
I don't know if we're supposed to only talk about optimization, or I was just, because I'm not really an expert in optimization. So, okay, great. Sure. So I could just say a few words about like my point of view about maybe this whole field of computing and just what kind of opportunities are available to us and how, different ways of thinking about it. So I just wrote a few pretty broad remarks. It would just be that from my point of view, I think there's a lot of attention on hardware. I don't just mean here, but I mean, you even hear this in broader conversations around like policy and governments, right? People will say, we better change our country's energy policy because we're going to have this hardware and we need more of it and it's going to use this much power. So we have to turn nuclear plants back on. I mean, these could be good things, but what I mean is there's very often an emphasis on hardware in the whole broader discussion of computing. And it can be easy to understand why, because you can look and see that there's some very exciting platforms that exist and that are being built and people here are developing and testing. So one thought I had was just, we want to always keep a balance there. I'm sure I'm speaking to the choir, all of you appreciate this, to also remember about the importance of algorithms. So the idea that even with kind of conventional computers, we're very, very far from knowing the limits of what they can do. They're, of course, ridiculously fast, right? The existing computer we have. So to a degree, it's really like what we're trying to do is kind of shed our own ignorance of how we're using them, right? Like, it's not that we really have my view is that we're probably making so many mistakes in how we're using them, and we could be doing it so much better. One way I think about it is the computer, in a way, it's kind of like the negative space in the painting. It's like you try to fill in as much as you can with your brain, and then the computer is kind of just the parts you didn't know how to fill in, and you're just like brute forcing through those parts or something. So it's kind of mopping up the part you didn't know how to think about, in some sense. Another kind of switching gears, another thing I was thinking about is the importance of empiricism. Again, I think this audience, I don't have to say this that much, but there can be a lot of discussions around advantages that want to try to find proofs and these kind of things, but they can often be overly idealized and overly broadly drawn. And when you actually start to kind of really try things out, you realize there's so many subcases of problems, and that's because of the existence of structure, right? Because in reality, there might be a class of problems that people might prove things about, but when you go to do things, you have your problem, right? You have the actual problem that you have. And then because it's your problem that got to you in its own quirky way, it'll have its own quirky details. And that's just what we would call structure, right? And then computing, and especially algorithms, gives us a way to then turn this back around and reorganize problems, I think, in a different way. And so instead of lumping them into broad classes and saying, these are hard, these are easy, or these are NP and these are P, we could say, these are easy for this kind of tensor network, or these are easy for this kind of sampling algorithm. And so it gives us all kinds of new theoretical perspectives to kind of more finely slice problems up, I would say. That's one other thought. One other last thought would be that hardness and easiness can be very relative to how we formulate the problem. So some examples would be, one thing I encounter in my field is just people will say, I want you to find the ground state. But if you actually kind of dig back into why they're saying that, it was just some lore from decades ago that they thought it would be easier. But actually, it's not easier sometimes. Sometimes finite temperature is easier, but people steer young people away from that because they say, well, don't start there because it's more complicated. But more complicated just might mean a few more extra things you have to put in your code. But then you give it to the computer, and the computer might be much happier. So just to say, we can often solve a different problem near the one we want to solve and get advantages that way. So, okay.
I'm gonna ask Ignacio to come up next. So let's see here. Oops. This is, which one was the roundtable?
Yes.
Yes, okay. All right, so now we'll do a screen share. There you go.
Okay. Let me see if I can put it full screen.
Okay. Thank you. Okay.
All right.
Well, hi, everybody. It's very refreshing to be here because I'm often in conferences where everything is AI. So now it's optimization. So I mean, I don't need to convince you that there are very important problems in optimization that have a very high value also. I work at a company that we're often do consulting work sort of in between companies that have interesting hardware that are looking for applications to it, and also companies that have hard problems and they're trying to see if they can solve them more efficiently. So I've gotten a bit of exposure on this side, and this is just a few things that I wanted to bring up that I think I've learned along the way, or that I think I've learned. First of all, I see is that there's very large, very high value problems that are very complicated. You don't really have a budget to it. You just need to solve it. And these require acres of compute, but there's also very small problems that are still hard. There's this LDPC, for example, is an NP-hard problem where you have a time budget in milliseconds and an energy budget in picojoules. So all of these things, I think, and there's obviously a spectrum all the way in between where I think there's a lot of space to play
I want to discuss 3 examples of projects that we worked on. This was a collaboration with NTT on a project proposed by BMW. And they have this pre-production problem where they need to build test vehicles before they start a new line of vehicles, and they have to pass thousands of tests. So they obviously want to build as few vehicles as possible and reuse them as much as possible with tests. And they said, can you use quantum hardware or quantum-inspired hardware? And it's just such a mind-bogglingly complicated problem because you had vehicles that needed to be destroyed, vehicles that had super complicated constraints, and even just building the vehicles had a lot of you couldn't build a 4-cylinder engine with a 6-cylinder engine, obviously. So what we figured out together with Yoshi's group was that you could separate a part of the problem where you can generate a ton of feasible vehicles that are buildable, that you don't have a 6-cylinder and an 8-cylinder engine, for example. And then you can use the coherent testing machines, for example, to do that. It's a maxat problem. And once you have a big library of those, then we uploaded these to, let's say, standard heuristics that were able to satisfy the constraints in the most efficient way. So we went from, I think this is what BMW was doing originally, where they could only solve a few constraints with a SAT solver. And then by doing this hybrid approach, and I think, anyway, this was an interesting lesson for me that you can, even in these complicated problems, there's often ways where you can find a niche or a spot. And it turned out that this was a very expensive part of their computation. So potentially this would be useful. This is another project that I worked on with Stephen Jordan when he was still at Microsoft. And the idea was they wanted to programmatically generate sequences for MRI machines. Normally, these are, it's a very complicated problem with a huge dimensional space. It's very expensive to calculate the objective function. And we ended up doing a simulation on all the little block spheres. We used a ton of compute. We couldn't really use any quantum or quantum-inspired hardware. But what we figured out was that quantum-inspired algorithms were actually the best tool that we could find for these problems. We tested a bunch of non-convex algorithms, and using some smart annealing, parallel tempering, population annealing heuristics gave us the best results. So sometimes the hardware is not there, but the lessons that we've learned along the way can be very useful. And here, this is something more recent that we've been working on. I want to discuss what I think the approach that I've seen often on the figure on the left shows it's a simple binary product circuit. This is, I think, a 2-bit by multiplying a 3-bit number. You can write it as a set of 15 Boolean operations. You see some XORs and some ANDs. And if you wanted to, for example, examine whether there is any faults within the circuit, this is one of those very high value, very expensive problems. One way that you could do it, you could convert it to a CNF problem and throw it into a SAT solver. If you had something, if you wanted to use an accelerator, let's say a few years ago, you would maybe map the SAT problem first to a Pubo, then the Pubo down convert it to a Cubo, and then throw it into your hardware accelerator and hope for the best. And we sort of went into a project that I'm going to discuss more on Friday, wanting to, let's say, skip as many of these layers as possible. So one of the things that we managed to do with the hardware I'm going to discuss on Friday was that we were able to stop at the CNF layer, and we have analog hardware using memristors that is able to natively solve a SAT problem with, let's say, it's called CLIMA for K-local. So it's natively high degree, and it also maps, it's also native on Pubos, but it turns out in this case that solving it in the CNF formulation was very efficient. We compared it with a Cubo and a Pubo formulation, and the fact that we are in native on SAT CNF also gave us access to the, let's say, the state-of-the-art heuristics on SAT problems that we were able to run on this hardware. And I think that was also very useful here. And the one last step, you notice in this native formulation that there's a bunch of XOR terms. So the last step that we've done lately is that we can even jump before converting to CNF. You can add support for XOR operations to your hardware, and this gives you a significant advantage. Not every problem has you have CNF problem that you can support, that you can solve also with an XOR solver. This was a very simple idea. We had problems such as this one, where some classes could be XOR, and we simply added support for the heuristic to recognize XOR classes, and we treated them in the exact same way as CNF classes. You did a stochastic local search heuristic. You flip a variable. If it helps you, and for people familiar with SAT heuristics, I can discuss this in a little bit more detail. But anyway, just from this simple change of supporting XOR operations in hardware, we were able to immediately see something like about 10 to 100x improvement over the same heuristic when mapped just on CNF. Okay, and the last thing I want to say, just to connect it to the original theme of that Shor's algorithm is not enough. One of the applications that maps well to this XOR conversion is something called the MAC-ELISE crypto system. It's one of the post-quantum crypto system that is, I think, currently just got approved by NIST for public key cryptography. This is all classical, but being able to solve it with non-conventional hardware allows us to essentially propose better bounds for this crypto system. That's it.
Okay, thanks. And Mahmoud is here, I believe. Let's see. Okay. Oops. Masood. Yeah. Okay. And let me see. I guess I need to do a share of that. Working? Yes. Okay, thank you.
Good afternoon, everyone. So, my name is Masood. I'm from the Electrical and Computer Engineering Department at the University of Pittsburgh. I don't have enough knowledge in the quantum mechanics. So, basically, I'm working in the optimization from the operational research point of view. So, I try to actually respect the title of the panel. And so I will present the outcome of my research group as well. So the optimization, we have seen the many application of the optimization, including the minimization of the cost function or the profit function with the subject to the set of the constraint in the different domains. But every day we have to actually solve the specific optimization problem in our real life. So, but the Shor algorithm is basically the one task that all of I'm sure you know better than me about the Shor algorithm is the one task and the integer factoring problem. But if we compare the optimization problem with the Shor algorithm, so the optimization problem can actually work and on the wide range of the application, and versus the Shor algorithm, that's the single purpose problem, just for the factoring the integer number. So the one question that at this point that we should answer that is which creates the recurrent values today, optimization problem or the Shor algorithm. So in my work, in my research work, I'm basically works on the application of the optimization problem in energy systems, and also enhance the quality of the solution result by the quantum computing. So I actually provided the two evidence in the energy systems from the Energy Information Association. It's talking about the energy system. Big energy system, independent system operator, works based on the electricity market. The main core of the electricity market is optimization problem. So the 5% improvement in the market efficiency leads to the billions of dollars in annual savings. For instance, if we actually improve the performance of the optimization tools in the electricity market algorithm, we have a benefit to the cost ratio tends to the 1,000 times benefits, which is very interesting for the energy systems. That's the reason why the optimization problem and increasing the quality of the result of the optimization problem is so important for the energy systems. So, on the other hand, the Shor algorithm drives a one-time shift to the post-quantum crypto. And if the RSA and also ECC retired, so we don't know what would be the application, what would be the convincing product of the Shor algorithms. So the majority of the researcher, in order to rely on the products of the Shor algorithm, is on the error corrections research. So, and in terms of the hardware readiness and the roadmaps, so for the optimization problem, and then by having the a couple of hundred to the couple of thousand qubits, so the hybrid QAO and also variational quantum linear solver accelerate optimization kernels, and also by taking the advantage of the GPU and the TPU plus the quantum inspired solver, this combination can deliver the benefits to the optimization society. But for the Shor algorithm, we need to around 1 million logical qubits and also having the full error corrections in order to have a successful Shor algorithm, which is not yet available. So, but the roadmap is so all of actually these reasons and justification implies that the quantum algorithm is the first real return on the quantum hardware. So when we talk about the quantum algorithm, we should discuss about the two types of the different algorithm: combinatorial algorithm and continuous optimization, combinatorial optimization and continuous optimizations. So if someone asks me, how do you feel the roadmap of the combinatorial optimization in the future in the operational research? If I want to choose the answer from the yes, no, or maybe, I choose the maybe. And also for the continuous optimizations, my answer would be something between the maybe and yes. We have more the promising insight from the continuous optimization based on the quantum computing algorithm. So why? Because with respect to the quantum computing algorithms, on the other hand, the classical algorithm outperforms, and they are both of these algorithms is growing up. And the researchers are working at the two different areas and the two different domains. And anytime they actually outperform each other. So we cannot say that the quantum computing algorithm for the optimization is better than the classical or classical better than the quantum algorithm. So, but the Shor just wanted to mention that based on the topic of the panel. So the Shor actually tricks has been used at the inside of the optimization or the subroutine of the optimization problem. But the fully Shor actually rarely called into the optimization problem. But for example, the phase estimation takes the advantage of the short tricks. And you know that the phase estimation is one of the backbone of the linear equation solver, or can be used in the HHNN and the quantum linear solver algorithm. And and also the linear equations can be used for the interior point method and also optimization inner loop, such as the interior point method algorithm, or any different version of the interior point method algorithm. Phase estimation also has another application in the amplitude estimation and stochastic optimization as well. Yeah, and so you can see the different list of the application in continuous optimization. We successfully ran the IPM interior point method inspire quantum computing for the 300 bus test system. We usually got the 30 or up to the 50% runtime cut and speed up. So that's the takeaway. So the big question is that, so we should actually, when we think about the optimization algorithm and also the Shor algorithm, we should think about this question, what kind of the investment has the earliest ROI rate of return of investment. So our intuition is that, or feeling is that definitely the optimization based on its application and also the future application of that. This is the possible question that we can ask the panelists. What real gains do we see today in the optimization, and what are the current challenges of the optimization tools? And because the optimization problem is not the easy problem, specifically in the quantum area. For instance, in order to load the parameter and also metrics information into the quantum algorithm, it's very time consuming, that can kill the speed up property of the quantum computing. And also, why cannot the Shor algorithm generate the ROI by setting the factoring as a services? That's the end of my talk. Thank you.
Okay, thank you. Let's thank all the panelists. Now we'll do the thing. We can all just sit in those chairs over there. And oops, stop share. In no particular order. Oh, yeah, well, no, that's the way we always do here. All right, so I want them to be able to see you, but if you want to sit there, that's okay. I'm just gonna have to rotate this around here. Okay, so the first thing we'll let you do is each panelist can ask another panelist a question. You don't have to, but if there's a question you would like to ask each other, let's start with that.
I have a general question. So many people have talked about structure, like justifying the good performance of metric product states and making the quantum simulation actually easier than they are. And that brings AI. So whenever there's structure, AI knows so well how to identify it. So there's another rival rather than quantum to our optimizers. So I wonder what people think about AI. I mean, some people integrated AI into their optimization, but just brute force AI, you don't understand anything, it just goes there and finds the structure. So are we worried?
Matthias Steuer just gave a very nice talk at New like a week and a half ago, and he was making the point that perhaps the quantum simulation, quantum computer can provide kind of the points in the training of AI with which the AI then will be able to produce the better results overall.
Everyone hear her with her back to you? Yeah. Okay. Unfortunately, you need to face them in order to be heard, so you just have to be all in the line. Sorry. You wanted to summarize that briefly?
Yes, again, it's not my idea. Matthew Steuer, that many of us probably know and read.
I'm gonna even let you pass this around there.
Really did a lot of benchmarking on D-Wave and this quantum versus optical discussion. And so his point was that he expects that the quantum simulations, quantum computers, perhaps would be capable of making small additions, so like very thorough calculation of the quantum behavior of a system during the AI training. And because of this little insertion, but AI then would be able to predict structures better and more informative. So rather than just doing all training on the possibility of running the quantum simulations just to train, just do it very specifically, very specialized, and that would dramatically improve the AI. That's
Would you like to talk about AI?
Sure, briefly. I mean, one thought sometimes I have to delineate what do people mean by AI, but like if we mean like things that start from sample, like data, and then does simple. If we mean that, then one thing I would say would be the kind of problems I know about is that I think there's a lot of opportunities, but it may not bring enough precision for some of the things we need to be a full replacement for like some of the activities we're using other algorithms for. So if we need, 8 digits of something, maybe, but I don't see it right now. I think a case would have to be made, but I could see it for useful things like maybe a kind of a silly example, but not so silly, would be telling us a more crude detail, like what topology of tensor network should we even try to, something more where there's more of like a binary answer or something where low precision data tells you the answer,
Did you want to talk about AI also?
No, but I can answer this question from the operational
Can you
research.
hand him the mic there? Yeah.
Okay. In the AI or optimization problem, so we can. So one of the key tasks is that based on the specific shape of the problem, for example, the type of the constraint and the type of the optimization problem. So one can recast a very tricky the structure of the optimization problem and solution methodology to solve that. I can give you one example. For instance, in the interior point method optimization problem, sometimes we actually struggle, and if you solve it with the HHNM or the quantum linear solver algorithm, it actually suffers from the key parameter of the optimization problem. For example, condition number, solution precisions, degree of the sparsity, and also a few more items. But it's very important. Recently, for example, we have developed an algorithm which is independent from the condition number. So we didn't do anything because I don't have knowledge in the hardware. I think other respected panelists do have, but I don't have any knowledge on the quantum hardware. But we try to actually come up with a robust solution methodology with designing the specific type of the algorithms in the
Did you want to jump in or?
Sure.
Yeah. How long is that? Yeah.
I'm not. I have to say I'm not very optimistic about. I've run some experiments on knapsack problems and problem salesman and read the literature, and I haven't really found anything that is super convincing for directly training AI to directly solve problems. What I've seen is I think the most successful efforts that I've seen is in the SAT field. There was some sort of Satinstein and Satzilla from the 2015s, where it was like a meta solver that had access to many different types of solvers and heuristics, and they trained AI. I think they weren't even calling it AI at the time, but this is what it was, on how to recognize which solver was going to be better for each specific type of problem. And they were very dominant at the time. I think that's not the case anymore, but these types of meta approaches, I think, would be.
Mhm. Okay, other questions from the panelists to each other?
Maybe?
Yeah, go ahead.
Yeah, but I mean, in optimization, particularly in combinatorial optimization, AI has been famously unsuccessful in solving all these NASA problems, right? And the Satzilla and the stuff that we talk about, the classification tasks, right? I believe that there are tasks where it makes sense to use certain algorithms, certain others has they fail their face. For classification, I would certainly use, I don't know, neural network, a support vector machine. But if I were solving a discrete optimization problem, that would be the last thing I would use. I'd rather use, I don't know, one of the simulated bifurcation machines or a branch and bound code. So I believe that, and this maybe boils back to your question of structure. The structure, what is the structure? It's just like features of the problem that we're dealing with and matching features of the problem that we're dealing with solution methods. I believe that that's where the actual potential lies. That's certainly, I think other speakers have already mentioned something along those lines. So, yeah.
But I don't think it's using AI to solve optimization problem. It's more like how to use machines or algorithms that can solve optimization problem to improve the work of AI.
Oh,
Right?
well,
How to, yes, how to improve your learning.
Exactly, right.
Neural networks, right?
Designing-
Because it's the same optimization problem at the end of the day, how to choose the parameters of the network in optimal way. That's optimization.
Sure, fair. It's not the same thing, right? If your training is massive grading descent, right? If you're hyperparameter training, you most likely don't know what it looks like. So people use like line plus optimization methods. So even within optimization, it's such a broad field that it requires specialization. Like answering the right questions. You need to spend a lot of time finding the right question that you need to answer, and most likely to answer it, you need the right tool. So unfortunately, it's not a single fit all solution, which thankfully, right?
No, but
that's the hardest.
there are very close
Yeah.
things. You do all these energy-based methods for the training of neural networks. That's precisely the problems that we are talking about.
Sure.
It's equilibrium propagation has a lot of elements.
Maybe we'll come to this. I mean, first one is we talk about optimization problems in AI. What about other problems?
Exactly, yeah, right.
The problem with protein coding was like a big issue, and then AI has effectively solved it, running to those. And the other thing I want to throw in is we talked about AI is component machine learning to predict quantum dynamics. The problem that we have is with quantum computers and quantum simulators. Generating training sets is very expensive.
That's what I'm saying.
So we cannot go in and say, okay, it's generally huge training set, and we have to like the implementation and we asking, okay, what data point do you now need next to improve your understanding of the system? Which data point do you now need? So I think that's a slightly different way of thinking about it.
And that's where the Matthias Roer comment comes in, right? You don't do it on the whole quantum generated sets. You just do it very strategically placed, just do those. But big question how.
Okay, so I saw both Masood and Miles have their hands up, so we'll go with you first. Yes, sir.
I think my question is that sometimes we should actually dissociate the two different concepts, quantum for optimization, optimization for quantum. But basically the majority of this actually discussion is based on the optimization for quantum. And it means that for the training the neural network with quantum circuits and finding the parameter of that. So we actually rely on the classical optimization problem. So, and one more question. Sorry about it. I have seen some current research on the quantum machine, QML, quantum machine learning. Instead of using the optimization problem, they actually parameterize the circuit with some specific stochastic and the randomized methods, but they don't solve any optimization problem. Do you, the panelists and also the audiences, do you have any information in this stuff?
No, let me pass it down to Miles here. Yeah.
Well, if anyone wanted to follow.
You want to
up,
answer his
everybody
question?
first. No, I don't know if I have an answer to that. Yeah, but your question was about what are people?
Just the mic is.
You're actually, what are people doing in these like optimizable circuits? Is that was your question?
Yeah, but instead of the running the optimization problem and also cost function or something, they actually parameterize the circuit based on the randomized techniques. It's very interesting.
I could mention one activity that I think is quite interesting that kind of ties optimization to learning, which is quite kind of cool. And in fact, it's been tried to optimize circuits, so that kind of ties into what you brought up. It's something that I want to try more. I've only played around with, but I haven't tried more. But it comes actually, you won't be surprised. It's related to a tensor network. It's sort of my obsession. But this comes from the math field, and it's this really beautiful type of machine learning called tensor cross interpolation. One thing that's beautiful about it is it doesn't have any gradient descent in it. So there's no optimization of that type. It's really just a series of low rank matrix factorizations that you do. And it's kind of an active learning method. And what it's very good at is learning high dimensional smooth functions. So if the functions are very rough or have lots of discontinuities, kind of forget about it. But if they're smooth, it's great. And it can be not highly non-convex, like you'd have tons of local minima and all this. And very often you can then represent the function. And that's kind of one hard part that it does really well. And the neat thing is once you have it in this form, it's like you've transformed it into this tensor network. Now sampling is easy. And sampling here means there's no Markov chain. There's no possibility of getting stuck. You can actually take true, totally uncorrelated draws that are true draws of the function that you learned. And so people have been trying this for optimization, where basically the sampling will just now sort of perfectly jump around to all the maxima of your function with high probability, and you can just kind of collect them all, compare their heights, and say there's the biggest one, and then zoom in on it. So this is a really, I think it's called TT-opt, tensor train optimization. But just to put that in people's minds as like the kinds of things that are possible now that weren't even like thinkable a few years ago.
About critical points, it knows the maximum.
It will, as long as it can learn the function, you can get the maximums, surely. Yeah. But it's sort of, it sort of ties optimization to like learnability in that case.
Did you have a comment, Wendell?
Yeah, just a high level comment. That one thing that gives me makes me smile every so often is there's so many like Ouroboros within this field. We are optimizing algorithms, and then we run a hyperparameter optimizer, and this itself is another algorithm, and maybe we just need to design chips to run the same algorithms again. So it's all feeding on each other. And it's hard to say at what point what is the like a solid basis that we can use to build to base everything off of.
So maybe this is a slight bounce off that. One of the take-home messages I got today was lots of people saying, well, certain machines are good for certain types of problems, right? And that, some platforms just won't be good for some. On the other hand, if we say we really care about optimization, like, are there any universal things we can say about optimization specifically that if you want to do standard industrial process optimization, like this is the way to go, or this is something we know, like, are there any universals that we can take home? Or is it like each optimization problem has to be addressed separately?
I think my lesson that I've seen so far, and I wouldn't say that it's universal or that's just on me, is that if you want to get the best performance, you have to be as native as possible on the problem. It's nice to have Groovy or even a fast Ising solver, but if you want state-of-the-art performance, you have to figure out a trick to really map the problem as close as possible to your hardware.
And this more or less resonates with the many what is called now quantum resource estimation. So the real quantum computers, people are really busy in estimating the resource and trying to predict what kind of applications will need resources that will exist maybe in 5 to 6 years and not in 20, 30 years. And not surprisingly, the first applications are the ones which are closer to physical systems. Like physics simulations, maybe materials, and maybe then the biological molecules, not too complicated. So that could imply that this is a native mapping. We have a physical quantum system and it has a native mapping to other physical systems. If you go to other, the overhead and the embedding becomes just so expensive, and that pushes, 10 years to the front. So maybe that applies also to our case.
No, don't feel that way.
I completely agree that, it should be solved natively, ideally, but there should still be some unifying platforms. And there should be good balance. So we know that if you just have Isaac and then nearest neighbor fraction of the square root, with a precision of 2 bits, then for the coupling, then you won't go far and you won't be interesting. But if and then the more you can do in terms of all-to-all Isaac would be step better. Precision is important issue here. To which extent you can vary the couplings reliably. This is extremely important. And then ideally, maybe within this hierarchy of different models, if you have K-local Hamiltonian, natively all-to-all, good range of precision for couplings, and good physical built-in capability of actually efficiently searching the low energy part of the spectrum, that's the route to success. Because then a lot of different problems can be mapped and can be solved almost natively. It will never be fully native. You still need to do some mapping, but that gives you huge variability of the machine.
Are there other questions back here? Okay, yeah.
There's a lot of people who are general quantum computing, quantum technologies. One big application that always comes up at the end, you mentioned so fast quantum chemistry. Finding new reactants, finding new drugs, finding new catalysts for various things. Would you substitute on optimization, or would you say this is a separate story all by itself that we have question?
To a large extent, that would be mapped into very high local connections. Local connectivity, I mean, you have polynomial objective with high order terms. And usually what comes from chemistry involves this high order terms. So they have to be something, in the kind of capabilities of the K-local Hamiltonian minimization. That comes from chemistry. That's how. I mean, if you have set, that's already 3 set. That's already natively cubic connectivity, right? But once you go to, and then it depends on the type of problems you're dealing with. But with chemical, then you go to very high locality, and then I don't know which machine actually is capable of doing that natively. But again, the mapping onto lower K is possible, but it comes at expense of increasing the number of spins, complexity, etc., etc. The complexity of the landscape, etc. But
Do you want to answer that question or ask?
Back to your questions. For example, traveling salesman problem, it has a standard shape, specifically in the structure of the construct. But it's very easy to define the traveling salesman problem in the quantum computing, because you can program how to import the information of the constraint into the quantum machine.
Sorry, as a penalty term or in its feasible formulation?
Classical form of the ESP.
But
the
with
n square,
with
the
a
n square overhead already
Yeah.
with the number of the series.
Counterexample.
It's a counterexample.
But the point is that this problem has been solved by the classical computer very well, and the optimality is less than 3% for the larger scale. But if you add one more constraint, we cannot claim that. For example, if you my point is that if you have a standard optimization problem, and if you can easily solve by the quantum computer, if you add one term into the objective function or into the constraint, you cannot, the previous general claim cannot be applied to the new problem, because you have changed the shape of the problem, condition number, and anything. So any problem should be actually analyzed individually for the individual machines. That's my approximate.
I have a comment kind of on that and the chemistry maybe. So my thought of a chemistry problem, or it's like kind of, I think there's a lesson in some work by someone I know, Steve White, working on chemistry, that I think often in computing, you can fall into a bit of a trap where you can sort of start to think a problem is hard, but it may only be hard down one branch of intellectual thought, right? So people go down one branch for a long time, and then it sort of hits a wall, and you go, this is a hard problem. And then whenever there's a problem like that, that's hard, it can be tempting to say, we need a quantum computer. But then I think already there's work showing that maybe the problem is the branch that we're on, not that the problem is so hard. So the branch that Steve White's been going down is to say, what if we actually use more basis functions instead of less? And to a lot of people in quantum chemistry, this sounds totally insane. And it kind of is insane at a first pass, because you go to them and say, how about instead of 100 basis functions, I'll give you 10,000. They look at their methods and they all scale like number of basis functions to the 6. So nobody wants to put 10,000 to the 6, right? But then the point is that if you trade off and you go to these more functions, all of a sudden you can have nice functions. They're highly local. They're these things called Gauss-Silts. They're local, they're orthogonal, they're compact. They have all the properties you could dream of having because they're based on these things called ternary wavelets. You have way more of them, but they're so nice that all of a sudden you can switch to a different algorithm. In this case, it's this kind of DMRG and MPOs that unlocks an entire new regime of scaling. So now you don't have n to the 6 anymore. You have 10,000 to the cube instead of 1,000 to the 6. Like you can totally reconfigure the problem. And now you can do, so what he was able to do with that were these 1,000-long hydrogen chain problems to way beyond chemical accuracy and rival other methods. So just to say that sometimes, it's too early to call a problem is all I'm saying. Yeah.
But also I can relate to
Okay.
what we do because we notice that spins, the number of spins is important because of scalability. But if you use 3 spins to represent 1, it means that you won't get stuck at the usual energy barriers when you have just scalar spins. So you increase by a factor of 3 your spins, but now you can easier find. The
So you make
solution
one thing
because
harder,
change-
you make the rest
Yes,
easier.
because the landscape changed and now you don't have this barrier. So that's very, again, there should be a lot of.
Yeah.
Okay, we got a question in the back.
Mhm.
It's very, very interesting discussion. I have a question about that. I don't want to be quantitative at all. I'm generally interested. So we have heard today about the simulated bifurcation machine, which I think is an amazing development, and which is still, I think, looking for its commercial application. And then we will hear about the periodized machine for NTT, which is also an amazing technology, which is also maybe less, I don't know, I'm just concerned with that, less looking for an application. And then we have 1 qubit that says that, or absolutely 1 qubit that says that we will still go with software and native, we're looking for the native description, and we don't think that the QUBO is interesting enough. My question is, how many orders of magnitude better does the hardware have to be in order for you to think that it's relevant? It's, because, yeah, I think it's 5 or 6 and what metric. I don't want you to be.
Yeah, no, I was thinking about that question. I think this is your question 1. So at what point do you define that you have an advantage over classical computing using, for example, our hardware is analog memory stores.
Well, the particular technology you mentioned was that.
Right.
But you're an algorithm.
We are working on a project right now on a software hardware co-development. That at least that's the latest things that I'm going to be talking about. There's going to be a talk on hot chips in a couple of months that's going to show the latest results. But let's say we see 4 orders of magnitude difference in energy to solution compared to the state-of-the-art solvers for let's say for SAT problems of size 150 or whatever. It's arguable whether these are commercially valuable problems. I think there is more commercial value or a path to commercialization than just in the QUBO space. But there is having hardware that is analog gives you, let's say, one-shot parallelization, meaning that you can compute the gradients in one iteration. So in 5 nanoseconds, you get the gradients for all your possible local moves. And this is at a cost of pico to nanojoules. So there's a massive advantage on classical hardware. Now, is this something? Can you draw the line and say this is analog advantage or analog supremacy?
So you think it's the energy, it's for wearables, it's for portable applications that the energy is important, so that's why this is pursued?
Right, yeah. To give you an example of an application, I think that's not the only scenario, but LDPC is a code that you use to when you transmit your messages from. Sorry, I'm not an electrical engineer by any means, but transmitting messages between your phone and a cell tower requires these modern codes because there's a lot of noise and the signal gets decoded at the tower and at your phone, and this is becoming more and more common with more modern protocols. And this needs to happen this is an NP-hard problem. There's linear versions, but you don't get very good signal. So there's a push to develop very energy efficient solvers that run on your edge hardware, if you want. That has to be, I think it's 1 millisecond and something like picojoules of budget to find a solution, to decode a message. And interestingly, I think this is also not too far from fitting in a Ising solver.
This is the MIMO problem, or?
This is the MIMO and LDPC I think fall within this small problems, hard, low energy.
That has to be solved both on the cell phone and the tower. Or...
LDPC, yes. MIMO, I'm not so sure. For sure in the tower.
Okay, let's go a couple more questions. So let's go.
Actually, I wanted to continue on Johan's question because this is an interesting question, and I rephrased it just now. Again, just looking at NTT and Toshiba, right? Because for me, I think it's just having 1,000 spins, classical spins, should be enough to solve interesting problems. And you have 100,000. So, but assuming that you can actually find the ground state, and I can give you an example. So I have my favorite problem, n-queens problem. So the problem of placing n-queens on n-by-n board in non-attacking positions, and queens attacking row columns and the diagonals. So if you start, so of course, as n grows, the number of solution grows, and it's an interesting problem. It's P sharp, doesn't matter. But if you start blocking the diagonals, you're not allowing the queens to be placed in particular diagonals, then if you block about n diagonals in n-by-n board, the problem becomes NP-hard. Because then probably you have only one solution, and that's it, and it's very difficult to find it. So the classical computers, at least by work of 2017, was able to go to which n? The audience, which n? What was the maximum n they could solve on classical computer? Lower, 21 to be exact. 21 n queens, just imagine 21 by 21, and it's already an unsolvable problem. But 21, if you map it into Ising, so you need one spin per each square, so that's n squared, so that's about 400. Okay, let's assume that from 2017, the computer industry moved up. Okay, not 400 spins, but 1,000 spins should be enough to tackle, I don't know, 24, 25 width. So why, with your 100,000 spins, guys, or 1 million spins, why can't you solve this problem?
But you need to find an absolute ground state for that.
Or just the transition, because what happens, but usually you need to just find the transition from easy when you find the solutions, and then there is a slope like phase transition, and then you cannot find solution because they don't exist. So just calculating the slope nicely, 1,000 spins should be enough. Mm-hmm.
The reason why they're not doing that is they don't have a customer that asks the solution.
It would be superiority claim, right? Classical computers cannot do, we can.
But how does that
Okay, over here.
No, but sorry, commercial application and winds, you place satellites in non-interfering positions. So in DNA, how you do the matching of the sequencing, no, there is a lot of it just cute formulation, but it has, it leads to the applications. Okay, yes,
Okay.
Hiroki.
Yeah, I mean, we know that, with the optimization is really hard. So we don't think that if a program is like this, higher than this, it's almost impossible to get that advanced. That's pretty clear, very nice, reasonable, approximate solution. Very quickly for the algebra, some application here.
Yes, just to you and then alternatives, folks that are solving public optimization problems, we recently put this intractable decathlon paper out there. It's not only us, but a bunch of folks and various institutions, including IBM, challenging both quantum and Tesla optimizers with 10 problems similar to what you described that are currently unsolvable, with some of them with actual money value of touch, right? To schedule the NSF and the NFL games here in the US that are completely trackable with moderately few variables. So if you're looking for card optimization problems, the whole field of operations research without needing to go to nonlinearities and ECOPF and you name it, we have already gathered really tough problems. So if you're looking for actual problems, I completely agree with you. There are some out there. We put them fully available. If you solve either of them, like at least you'll get a price. I'll give you a copy of pricing by later.
No, it goes under umbrella vehicle routing problem.
We
And
have
then
some-
instead of travel salesman, you have really hard problem with just you.
that's one of the 10.
Okay, we've gone a while. Let me make it parting shots. Okay, anyone want to make a last comment before we close? Let me just open up a can of worms myself.
Maybe just a quick one. These problems, maybe I didn't understand problems like that one lot, but they sound kind of like problems that AI would have a good time with, because you can generate so much data with so many different.
But there is no logic, it's just exponential growth, and it's like searching for, you can barely come up with anything rather than exhaustive search.
You can try AI with massive
Yeah.
data with different.
They're very unstructured problems, that's the key. So you cannot even predict, like how many solutions you have, not mentioning, when you start kind of randomly imposing the
Am
constraint.
I also understanding that it's hard to tell if you're close to a solution?
Yeah.
Is that right? Like you might be sort of technically close,
Yeah.
but there's not a lot of information to
have
say, just
one-
move over.
Let's say one queen is misplaced, but you have to follow those to actually place the queen. So yeah.
Okay, well, let's thank all the panelists again. Thank you for a lively discussion, and we'll see you all at 9:30 tomorrow morning.
Yeah.